So in this video I'm going to go through the answers for exercise 2 from 17.1, which is all based on mass spectrometry. Just at the top here I've written down the mass of some common fragments that you'll see in organic chemistry. So a fragment with a mass of 15 is typically a CH3, fragment with a mass of 29 is typically C2H5, and then with 43 is typically C3H7, although that can be written in more than one way. It could be a CH3, a CH, and a CH3, but it's typically C3H7, although that is not the only option, as we're going to see. In the first question, I give you 2 aminopropane, and I give you 4 different peaks, and I ask you to come up with fragments that will be responsible for those peaks. Okay, so the first peak I give you has a mass of 15. We've just seen that 15 is typically a CH3. I need to confirm that it is possible to break a CH3 off the molecule. So if I have a look here at the molecule, if I were to break this bond here, then I would produce a CH3 fragment. I would also produce an NH2CH3 fragment. If the positive charge were to stay with the CH3 fragment, I would end up with a peak at 15 because the formula mass of CH3 is 15. If the positive charge were to stay with the NH2CH3 fragment, I would end up with a peak at 44 because that is the mass of this fragment. Okay, so remember your molecular ion is unstable and it will fragment. It can fragment anywhere and it can fragment multiple times, but at A level you're only going to be asked for one fragmentation. When it fragments, you end up with a positively charged ion and a radical. If the positive charge were to stay with the CH3, you would get this peak. If the positive charge stayed with the this fragment, you get this peak here at 44. So either ion is possible if that bond were to break. You could also break this bond here, and you're going to get exactly the same thing. If we look at our next fragment, it's 16, okay? So 16 is not one of our common fragments, so you're going to need to have a look and see if you can figure it out from the molecule that you've got. So I'm drawn to the NH2 here, okay? Nitrogen has a mass of 14, each hydrogen has a mass of 1, so NH2 does have a mass of 14. That means if I were to break this bond here, I would end up with an NH2 fragment with a total mass of 16, and I would end up with a CH3 fragment with a mass of 43. So we've already seen that this fragment here, C3H7, has a mass of 43. So again, if you were to break that bond, you end up with a positive charged ion and a radical, but either fragment can be the positively charged ion, so you are going to end up with both peaks. Okay, so they're the 4 peaks that you get from 2-aminopropane. In question 2, I then ask you to have a look at 1-aminopropane. So these guys are isomers. They have the same formula mass, so they both have a formula mass of 59. And I asked you what fragments are common to both and what fragments are unique to 1-aminopropane. So if I have a look at the fragments that are common to both, okay, so we saw above that the peak at 15 was caused by a CH3. If I look at my 1-aminopropane, if I were to break this bond right here, I can break a CH3 off my molecule, therefore it's also likely that I get a peak at 15 in 1-aminopropane. If I break a CH3, which has a mass of 15, then I'm going to be left with this fragment here, which has a mass of 44. So the 2 fragments have to add up to the total formula mass, which is 59. So I break this first bond, CH3, and then this fragment here, giving me these 2 peaks, just as I had in 2-aminopropane. I could go down here to this bond, okay, and I could remove an NH2 just as I did above. If I remove an NH2, again, I'm going to have I won't have a 14, I'm going to have a peak at 16. So 14 for the nitrogen and 1 for each hydrogen gives me a peak at 16, and then the remaining part of the fragment is going to be have a mass of 43, giving me a peak at 43, again, just as I had above. So these 4 peaks are common to both molecules. However, you are also asked for a peak that is unique to 1-aminopropane. And if I break this middle bond here, I end up with a C2H5, which has a mass of 29, and I end up with a CH2NH2 with a mass of 30. These 2 peaks are unique to 1-aminopropane. Because if I move here to 2-aminopropane, there is no bond that I can break that gives me a fragment of exactly 29. So I know you've got two carbons bonded together, so you might think it's possible, but to have those two carbons by themselves, I'd need to break 2 bonds, okay? And even if I did that, even if I were to break both of those bonds, I wouldn't be left with a CH3CH2, I would be left with a CH3CH, giving me a total mass of 28, not 29, okay? So this fragment here is not possible. And if you can't remove a fragment with a mass of 29, then you're also not going to be able to remove a fragment with a mass of 30. These two fragments are linked. They go together to give you the total mass of 59. So these two are unique. Question 3, similar style question, okay? Except over here, the fragments that I've given you, the masses of those fragments aren't any of the common numbers that we often come across in mass spec. When this is the case, when you get a number that you're not familiar with, the best thing you can do is see what you have lost from the molecule. So this here is my ester. It's got a total mass of 88. If there's a peak at 73, then that must mean I've lost something with a mass of 15. Now 15 is a mass that I'm familiar with. 15 is typically a CH3. And if I look at my molecule, I see yes, if I break this bond right here, and I remove a CH3 with a mass of 15, then my remaining fragment is going to have a mass of 73. And this here will be my remaining fragment with a mass of 73. Okay, you could also have taken the CH3 from the other side, okay, and then you would have been left with this fragment here, which would also have a mass of 73. The next, again, 59, not a number we're familiar with, so we'll apply the same approach. We'll take the total mass, 88, we'll remove the 59, and we'll see that something was removed that had a mass of 29. A 29 is a number we're familiar with. It's typically C2H5. And if I look at my molecule and break it right here, I can remove 2 carbons and 5 hydrogens, which have a combined mass of 29. If I do that, the fragment that I'm left with has a mass of 59, which is the peak that I asked you about. The last bit, 45, again, not a number that we're familiar with, so we're going to apply the same approach. Okay, if I were to have a peak at 45, then I must have lost 43. Now, 43 is a number we've come across, and it's typically caused by a C3H7, so a propyl group, 3 carbons, 7 hydrogens. And that propyl group can be arranged as CH3CH3, or as CH3CH2CH2. But if I come here and I look at my molecule, I will see that I don't have 3 carbons connected to each other. So I've got no way of removing C3H7, even though it's a fragment that commonly appears in organic, in your mass spectrometry. So what that tells me is that it's not my common peak, it must be something else. So in this case, you might have to use a little bit of trial and error. So what I've done here is I've already broken this bond and I've broken this bond, so I'm just going to keep going and I'm going to try break this bond and I'll see what I'm left with. So if I break that bond just there, what fragments do I end up with? Well, I end up with this fragment here, which has a mass of 43, and this fragment here, which would have a mass of 45. Now that is what you were asked about. You're asked for a fragment that has a mass of 45, okay? So even though 43 is commonly C3H7, it's not always C3H7. A CH3 bonded to a carbonyl group has exactly the same formula mass, okay? And then the other peak there would be 45. Now, just again, to fully clarify, when you are breaking a bond, you don't end up with 2 positive ions, okay? You end up with 1 positive ion and a radical. But that positive charge could stay with either fragment, which is why I'm drawing both possibilities. They don't both happen at the same time, but either either fragment is possible, therefore I'm including all possibilities for what you might see on a mass spec. Question 4 is similar. to question 2. So I give you buthanoic acid, so I give you the carboxylic acid, and I ask you to compare it to the ester. If you look through the fragments that we've already seen above, you'll see that, for the most part, they are all possible for the acid too. I can remove a CH3 and I'm left with this fragment here with a mass of 73. I can remove a C2H5 and I'm left with this fragment here, which has a mass of 59. So different to the fragments that we got from the ester, but still with the same formula mass. Therefore, you'll get a peak in the same place. You can also remove a peak at 43. Again, this is different from the peak that we removed from the ester. Instead of having a CH3CO, I am now removing a propyl group, C3H7. But these peaks will look the same on a mass spec. They've got the same formula mass, so it doesn't matter that they're caused by different atoms. They will appear in the same place. And then I have this COOH group at 45 instead of what I had up here. But again, still 2 peaks in the same place, even though they're caused by different fragments. A peak that's unique to your carboxylic acid, however, is your OH, okay? If I were to break this final bond here, I would remove an OH. Oxygen has a mass of 16, hydrogen has a mass of 1, gives me a peak at 17. If I look at my ester, I can't remove an OH. There is no hydrogens bonded to the oxygen, so I'm not going to have a peak at 17. And if I can't remove a fragment with a mass of 17, then I'm also not going to have a fragment with a mass of 71, okay? The total mass is 88. If I remove 17, I'm left with 71, and that will be this fragment here. And both of these are unique to buthanoic acid. The next question is question 5, and I give you 2-methyl 2-iodopropane. I told you that there was a peak at 169. Again, not a number you're going to be familiar with, but if you use the total formula mass of the molecule, you will see that this has lost a CH3. It's lost something with a mass of 15, so it's lost a CH3. So if I take my molecule and I remove one of the CH3s, what I'm left with is we'll have a mass of 169, and it will be the fragment that I'm looking for. On the other side, again, not numbers that you're going to be familiar with. I've got a peak at 57, and if you use the formula mass of the molecule, you will see you've lost something with a mass of 127. Not a number you're familiar with, but if you look at the molecule and then look at your periodic table, you should see that iodine itself has a mass of 127. So if you just remove the iodine, what you are left with, the carbon, the alkyl portion, has a mass of 57, and that would be the fragment responsible for that peak. Again, it doesn't matter what way you're drawing these. You can use structural formula if you prefer. It doesn't matter where on the molecule you put the positive charge, as long as you're including the positive charge. So question 6 then, I ask you to compare. I think it is iodobutane with your 2-methyl 2-iodopropane, and give me fragments that are common to both. You can get a fragment at MZ29 in both. You can get a fragment of MZ43 in both. Sorry, I've just gone back to read the actual question. I asked you for peaks that you would find on 1-iodobutane that you would not find on your 2-methyl 2-iodopropane. So these are the peaks that you will find on 1-iodobutane. You can break off a CH3CH2 fragment with a mass of 29. You can break off a C3H7 fragment with a mass of 43. And if you're breaking off this 29 portion, you're also going to be left with this portion here at 155. And if you're breaking off a fragment with a mass of 43, you're going to be left with this fragment here of 141. And all of these peaks are unique to 1-iodobutane. Question 7 is slightly different. In question 7, I ask you to calculate the molecular formula for me. So this is something you would have done at GCSE, and you would have done it at the start of last year, I think. You take your empirical formula, which you're given in the question, and you find the relative formula mass. So you're given the empirical formula C3H7Br. You find the relative formula mass of that, it's 123. Then you look at the relative formula mass that you're given in the question. Now in this case, the relative formula mass of the empirical formula that you just calculated and the mass that you're given in the question are exactly the same. that means that your empirical formula and your molecular formula are the same. Okay, but you do need to show me how you use those numbers. They often do this in the exam questions. They'll get you to show how you work it out, and if you don't show what you've done, you won't get the mark even if you're using the right molecular formula. So I take my answer 123, I divide by the answer I'm given in the question. I end up with an answer of 1. I multiply that by my empirical formula, and what I end up with is my molecular formula. So it's just important in this one that you show you're working. Then you're asked to draw possible structures. So C3H7, or you can draw it as 1 bromopropane or 2 bromopropane. And then you're asked to look at the fragments that you've got and decide whether your molecule is 1 bromo or 2 bromo. So the first fragment is at 15. If it's at 15, I'm expecting a CH3 group. Okay, if I look at my 1 bromopropane, I can break this bond right here and break off a CH3. So I'm likely to get a CH3 fragment from this molecule. If I move over to my other molecule, I could break this bond right here and get a CH3. So I'm likely to get that fragment from both molecules, giving me a peak at 15. If I look at the next one, 29, that's typically caused by C2H5, all right? If I were to break this bond right here, I would get a fragment with a mass of 29. So I'm likely to see this peak for 1 bromopropane. However, if I move over here, there's not one bond I can break that will give me this peak, okay? If I were to pull off the bromine, I'm left with 3 carbons, not 2. If I were to pull off the CH3 and this bromine, I'm left with a CH3CH, which would give me a mass of 28. Plus, I can't break 2 bonds, I'm only breaking 1. So I'm not going to see this peak if I've got 2 bromopropane. If I look at my final peak, a mass of 43, okay, typically C3H7. If I were to break this bond right here, I would get that fragment. If I were to break this bond right here, I would get that fragment. So I'd expect a peak at 15 and a peak at 43 for both molecules, but I would only expect that peak at 29 for 1 bromopropane. Therefore, molecule A must be 1 bromopropane. Question 8 is a similar story. I find the relative formula mass. It matches the formula mass of the molecule. Therefore, the empirical formula and the molecular formula are the same, but I need to show that. I draw out my 2 possibilities. I've got propan-1-ol, I've got propan-2-ol, and then I analyze the peaks. First peak is at 15, typically from a CH3. Both molecules can give me a CH3. Both molecules are likely to produce that peak. The next one, a peak of 29. My propan-1-ol can give me a peak of 29. If I break this bond right here, I'm breaking off a C2H5, which is a mass of 29. However, I cannot get a fragment with a mass of 29 from my propan-2-ol. Okay, I would need to pull off the OH and the CH3, and again, I'd be left with a CH3CH, a mass of 28. So I can't get a fragment with a mass of 29 by breaking just 1 bond on my propan-2-ol. I can get a peak with a mass of 43 from both. I can pull the OH off the end here and the OH off the top here. I'm left with C3H7 in both molecules, giving me a mass of 43. Okay, but because this peak at 29 is unique to my propan-1-ol, propan-1-ol must be molecule B. Question 9, another similar one. I find my formula mass, it's 44. This time it does not match the mass I'm given in my question. So I'm told that the formula mass of the whole molecule is 88. So I take that, I divide by the formula mass of my empirical formula. I end up with 2. I then take that number and multiply by my empirical formula that I'm given in the question, and this is my molecular formula. So my molecular formula is different to my empirical formula in this case. I then use this to draw out possibilities. So I've got my acid here, and then I've got another acid here. So I've got 2-methyl propanoic acid compared to buthanoic acid. And again, I analyze my fragments. CH3, they will both give me a CH3. Okay, I can break this bond here to get a CH3. I could break this one or this one to get a CH3. The next one, mass of 59. So again, that's not really a fragment that you'd be familiar with. But if you look at the total mass, you will see that it's lost something with a mass of 29, and we are familiar with 29. It's typically C2H5. So if I come over here, can I remove C2H5? Yes, I can, meaning this molecule is likely to give me that fragment. Can I remove something with a mass of exactly 29 over here? Well, I can't remove just a C2H5. If I break this bond here, I'm left with 3 carbons, not just 2, okay? And the last one I've got is MZ is 43. This is something I'm familiar with. It is my C3H7. I could break this bond right here and get C3H7. I could break this bond right here and get C3H7. So both molecules are giving me that. So again, it's this middle peak here that is unique to just my butanoic acid, okay? I can't remove something with a mass of 29 from my other acid, therefore I do not have a peak with 59. Therefore, molecule C is going to be butanoic acid. And one more, exactly the same thing, find the formula mass. I show that the molecular formula and the empirical formula are the same thing. And then I ask you to, what have I asked you to do? Because this question is slightly different because I ask you to suggest a structure for molecule D. So I tell you in the question that molecule D can be oxidized to form a ketone. So if it's oxidized to form a ketone, then it must be a secondary alcohol. I also tell you that it's branched. And I tell you that you've got 2 peaks in there, a peak at 43 and a peak at 45. So we've seen 43 before. It's typically C3H7. And if you look at the total mass of the molecule 88, you will see that if you're losing a C3H7, what you are left with has a mass of 45. So again, this one, it's just going to be a little bit of trial and error, okay? You need to use the information I've given you in the question. You know it's a secondary alcohol and you know that it's branched, okay? So if you were to, actually, I'll do this on a piece of paper. We'll look at some possibilities, all right? If you know you've got 5 carbons, all right, so if I drew all 5 carbons in a row, okay, even if I'm making that a secondary alcohol, it's not branched, okay? So I have to have max 4 carbons in a row in order for it to be branched. I need this to be a secondary alcohol, so I can't put the OH on the end, so I'm going to put it here, okay? And I need to put my branch someplace. If I put my branch on carbon 1 or carbon 4, well, then I'm just making it a 5 carbon chain again. So I can put it here, or I could put it on the same carbon that has the OH group, okay? If I put it here, I've still got my secondary alcohol that can be oxidized to a ketone. If I were to put my branch on the same carbon as the OH, well, I've just turned this into a tertiary alcohol, okay? So this carbon here is now bonded to 1, 2, 3 carbons. It is tertiary and it cannot be oxidized. So before I even look at my mass spec data, by just doing a little bit of trial and error, this is my only possibility as a secondary alcohol with that molecular formula that is branched. If I then look at my mass spec data, I will see that it fits because I know I need to be able to break off a C3H7 to give me the mass of 43. If I break this bond here, I'm pulling off C3H7, which gives me a mass of 43 from this fragment, and the remaining fragment would have a mass of 45. That's all the answers. If you've got any other questions, let me know. But mass spec just takes a little bit of practice. The more questions you do, the more familiar you will become with how to answer them and how to approach them.